Great, thank you. So the focus of my talk is on the restoration of narrow riparian tree buffers, like you see in this picture, back from a time last spring, when California was actually green. Riparian tree restoration, as I'm sure this audience is aware, is a really widely used type of restoration intervention, particularly in agricultural systems. And there are good reasons for this. It has the potential to restore some ecological functioning for a relatively low cost. And when I say ecological functioning, I'm talking about things like biogeochemical processing, habitat for species like birds and fish, aquatic insects, amphibians, and it also provides connectivity across landscapes that can otherwise be quite fragmented. But the research on this topic has also shown that results from these interventions are mixed. They don't always perform as well as we'd like them to. And increasingly we're understanding that one of the reasons for this is that the context in which they take place and the details of the restoration itself can make a difference. So this is an image of one of the stream buffers that I worked on, and you can see that the dark green of the restored treed area stands out in really stark contrast to the surroundings, which in this case are grazed. So one of the things that we clearly need to think about at this site, as we've heard a lot of talks about in these 2 days, is sort of the condition of the surroundings and the watershed and everything that might be draining to this point and contributing stressors, and possibly limiting potential recovery at that site. But there are also details of the restoration intervention itself that it's important to think about. So that's things like the width of the restoration, which has been quite thoroughly studied. And people have found that wider buffer zones, which in many cases is set at greater than 30 meters of width, have the potential to provide benefits like nutrient processing and water filtration. And they also provide important lateral connectivity from the stream channel to the banks and the surroundings. But what I'm going to focus on today is a different dimension of this riparian buffer, and that's the length, the linear buffer length. And longer buffers also have the potential to improve benefits even in cases where the buffers are quite narrow because they're extending the length of shading. So when you have a greater extent of shading, it can help with temperature regulation, a longer area with more complex channel and better habitat. It can also cause a shift in food resources from algae and the more sunny sites to leaf litter potentially, and it provides more of this longitudinal connectivity. The questions that I'm focusing on today are first, which aspects of stream condition can be improved with the restoration of narrow buffers? And second, do longer buffer lengths result in greater improvements? This is a picture of another one of the sites where I'm working, and you can see that this buffer is quite narrow. The buffers in the systems I worked on were all substantially below that 30-meter threshold. They were in the range of 10 to 15 meters wide. And you can see here it's this narrow band of willows with a fence along the outside to exclude the cattle, which you can see grazing in this field. And it's a pretty homogeneous landscape of pasture. I chose to work in these study sites, which are in West Marin in California, like an hour west of here, because they have a very consistent land use of rangelands across a pretty large area where I could find a series of second through fourth order streams to sample on. And there also has been a lot of focus on restoration and improving water quality and habitat in these systems. And there have been a lot of restoration projects, a lot supported by folks at the RCD and the state, and these have been, I was able to choose from a selection of sites where the restoration had been completed more than 7 years ago to give the trees time to establish and the stream some time to recover. This map shows the location of the sites. Each dot is a different sampling site. There are 25 in total, spread across West Marin County, and you can see that they're arranged in clusters. If we zoom into one of those clusters, it looks like this. So each of these yellow squares is a different one of my sampling sites. And I chose my sites so that I could have one upstream site without restoration, and then additional sites downstream within an area that did have trees as a way of isolating the effect of the trees on the stream. So the primary predictor variable I'm looking at here is buffer length, shown along the left side with those numbers. So I'm able to compare conditions in site 1 to site 2 to site 3 to see if there is an improvement or change. And my 25 sites were nested into 8 of these clusters. At each of the sites, I collected data on channel form, substrate size, specific conductivity, which we heard about earlier, water temperature using temperature loggers, and I also looked at percent cover of aquatic vegetation, organic debris and wood in the channel, and I collected benthic macroinvertebrate samples. Today I'm going to be focusing on 3 metrics that I calculated from those samples, and those are density, which I would expect to decline with more shading, less sun, less algae, and then richness and percent sensitive taxa. And the percent sensitive is the same looking at the intolerant taxa in the sample, so 0 to 2 on a scale of 0 to 10 in terms of their tolerance of stress and fine sediment. And I would expect both of those to increase if you do indeed have better conditions for the macroinvertebrates as you move further downstream. So just to show what some of these paired sites look like, on the left we have the site that does not have the restoration and is open, and then this is the same stream, in this case just a couple hundred meters downstream. And you can see that the willows grow up very densely in a lot of these sites. It looks quite different. Here's another site where we have the stream is much wider. We have alders instead of willows. It's still a very narrow buffer. Okay, so moving on to some of the findings and the data portion. I'm going to be looking at the response of in-stream conditions to different scales of influence. So the watershed scale, the watershed condition being the controlling feature, the riparian buffer length being important, or simply a response to riparian buffer presence and absence. And just as a note, most of the data I'm presenting today are from 2015. I also resampled in 2016, and I've processed about 80% of the samples from the sites I revisited. So I'm going to be talking about that a little bit as well. So I'm able to contrast 2 years of pretty different conditions with that. To get a sense for how the sites are doing overall, I used the family level version of the CSCI tool to calculate scores for all of my sites. Each color is a different stream, and each bar is a different site within that stream. And you can see there's a big range in CSCI scores that I got across my sites, but all of them are quite low. They ranged from 0.3 to 0.8. So these are streams that are likely feeling the impact of the grazing. It makes sense given the pretty transformed landscape that surrounds them. And I found really similar patterns in scores between 2015 and 2016 data. So this is a graph I'm going to be using for the presentation of a lot of the data. So just to walk through it briefly, on the x-axis I have meters of upstream buffer from 0 to 2000, and then as you move left to right, you're moving downstream to sites that I'm hypothesizing will have higher condition. So there were some metrics that were really controlled by conditions at the watershed scale. In my sites, my major water quality metric was looking at conductivity, and in this figure, each line is a different watershed, and you can see that there is really no movement with buffer or buffer length or buffer presence, and that intervention is not affecting conductivity at those sites. But each stream is looking quite different. However, I did have some metrics that responded to buffer length. My percent sensitive taxa metric, for example. So again, each line is a different stream, and you can see that the slopes are quite different. Like the pink one has a really extreme increase as you move downstream, even though it's not moving downstream that much. But then some of the others have a very shallow slope, but overall you are seeing, I did see a positive trend with buffer length. Comparing, that was the 2015 data, comparing that to the 2016 data. The 2015 data is kind of like faded out behind it, but you can see that there are similar patterns. So the pink site is not quite as high, but still heading up. This green site is falling very similarly on the same line. And when I fit a mixed-mix model to the 2015 data, I found an increase. It was a significant increase in condition in percent of sensitive taxa with as you move downstream and had more upstream buffer. I found similar responses for density and temperature. Both density and temperature declined with increasing lengths of upstream buffer. So at least for these 3 metrics, the length of the buffer does seem to be important. There were also some metrics that did seem to be responding mostly to buffer presence rather than length. They just cared, are there trees or no trees? So Smallwood was one of these examples. If I just plot all of my data with the sites, it's extremely messy. And it seems like some go up and then they go down again after you have more buffer, and it's a little bit, there are a lot of different patterns going on. So I took the approach of reducing it, so I was just looking at the most upstream site and then the closest downstream site. And when I did that, I found a really clear pattern where you are seeing more Smallwood in sites that have trees versus not, which is great. I feel like if it was not that way, I'd be very confused. And I found the same, a similar pattern of response for percent macrophyte cover in the channel, except for in that case I saw a decrease. So I'm seeing less vegetation in the stream in sites with trees. Again, making sense because these are streams that are shaded. So to pull some of this together, I did see different modes of response depending on the indicator that I was looking for in the streams, indicating that these different scales of management are all really important at these sites. I saw some metrics that really did not respond to the intervention and seemed to be controlled by the watershed scale. So the scale that they're working at is not affecting these responses. I saw some that did seem to really respond to buffer length. So proportion sensitive families, abundance, and temperature all were responding to greater buffer length and greater extensive shading. And then some seem to really mostly be affected by buffer presence and absence, at least in the sites that I was looking at. There's a fourth category that I didn't talk about today, where the patterns varied a lot by site and didn't seem to be clearly responding to either. And this was substrate size, insect family richness for my 2015 data. And I'd also like to note that as I summarize, that the 2015 and 2016 insect data so far are looking very consistent, despite the fact that 2015 was an extremely dry year, and 2016 was a more normal rainfall year for Marin County, even though the rain came somewhat late. So, in conclusion, we found that buffers did have some positive effects on stream ecosystems, even short and narrow buffers, but that longer buffers can be better than shorter and affected a broader variety of measures of ecosystem condition. We also found that in this landscape, some metrics did not respond at all to the restoration, and so it's important to be realistic about the gains that are likely to be achievable given the scale of restoration you can do and the resources and the initial condition of the stream. And then finally, we found that patterns were pretty robust across years of quite different rainfall. And with that, I would like to thank you all and take any questions.
Yeah, I have a question, but I'll share some information that will be of value to you.
That'd be great.
I think
here at the UC Davis Agronomy Department about 15 years ago, I think his name was Dr. George or Dr. McGeorge did a similar study on buffers for grazing. Also about a dozen years ago, the Leopold Center for Sustainable Agriculture at Iowa State funded a similar study with buffers. And the USDA NRCS has a standard for those buffer strips that might be worth looking at. You probably know that.
Yeah.
And if you want any more details on this, you can see me at 4 o'clock or something, or give me your email address and I'll share some more with you.
Sounds great, thank you. Was there another? Are we out of time? Okay.